Continue. Hey, hello everyone who is watching us offline. We're having tea. You should have some tea too. Lecture 10 in high-dimensional probability. So last class, I think the main concept that we tried to put in our heads is that when we sample something, when we take a sample from a population, how good is that sample? It can be good for specific tasks, such as, well, we can estimate the mean, for example. We can estimate the variance. We can learn a lot about population from a sample. True, that's what statistics is for, right? How do you learn about something just by taking random sample? Okay. What you can't do, and this is sometimes that people don't understand that, what you can't do is hope that the sample would be able to answer any kind of statistical questions with reasonable accuracy. So you can ask a lot of statistical questions and hoping that it would reflect all possible statistical properties. And this comes in the following form of a counterexample, that very clear counterexample that we gave last time. If we throw n points, so last time, if you throw n points into a square, let's say unit square, the unit square 1, 0, 1 to the square, independently, just like that. I'm just throwing independent points. Then, for any set I, such as this one, for any set I, the number of points in I is proportional to the area of I with high probability, with reasonable probability. And we'll make this statement again very accurate later, but the idea is that if you sample, any sample will be kind of representative. That is true. However, I can always build a kind of a alleged counterexample to this. I can deliberately avoid these points and still make, how do you do that? Okay, maybe like that. I can make this octopus avoid these points and still make the area very large. So on the surface, the set contradicts what I just said. Right? We sample these points, and there are some statistical questions in the form of this I prime that the sample does not answer correctly. Right? The sampling procedure does not answer correctly because I prime does not have any points, and yet it has large area. That's a contradiction to this statement. Then we figured out why this contradiction isn't, well, it's not a contradiction, it's a paradox, I guess. Why this paradox is not a formal contradiction. What happens is that I first have to formulate my task, which is I, and then I take the sample. Then we're fine. We're not fine if I first take the sample, I look at the sample, and then I formulate my question I. Because then I can look at the points and maybe I'm some adversary, right? Look at the points and deliberately do something. So the set, so it is true, the instance results come in this form with high probability, and I just write WHP, with high probability, the statistical answer is correct. No, sorry, that's not true. First, we said the question, right? For any I, this is correct with high probability. This is an instance result because it applies to a given I. I first fix I, and then I say with high probability for this specific I, everything is fine. True. The uniform results say that with high probability, the statistical answers will be correct for any kind of end, for any kind of question. So star holds for any I. False. I prime is a counterexample. So the uniform result, do you see the difference? It's a quantifier that's a difference, but what really is false is that with high probability, I want the sample to be true for whatever task. That's not going to happen. Okay. Not going to happen, but we want to do that, right? Don't we? How can we first formulate the question and then take the sample? Maybe we know what we want to study in the beginning, but maybe we don't. Maybe we just take a census, you know, to take the population sample. And then we think, okay, maybe it looks like, you know, COVID depends on the age here, right? So let's run this regression. Can we do that? Well, formally we can't, because we first saw the sample. From the sample, we guessed that the COVID is looks like correlated with age, and then we are trying to prove that. That falls into the uniform result. It's formally false. Right? You can do that. But people do this all the time, don't they? This is data mining. That's exactly the data mining. You look at the data. From the data, you see some patterns, and you try then to justify them. But you can't have that because uniform results are false. So how something is really breaking really bad here. The whole statistics is breaking really bad unless there is a way around. And the way around, as we is to include only, well, the way around is to say something like this. Well, your octopus is really, really pathological, right? You had to really work hard to present this counterexample. Usually the normal statistical tasks are not like that. It's not like the adversary is trying to build a very, very nasty counterexample. It's we who are doing just normal regression. It's not an octopus. So the way around is to say, is to include only simple tasks, relatively simple tasks. Include only simple sets I in the uniform results. And then it becomes possible. Then uniform results becomes possible. And I here note that I careful not to write they become true because it depends on what we mean by simple here. And the simple way, Oksana, for example, she suggested last time convexity as a measure of simplicity, right? Convex sets are simple; they're not like this octopus. And I still don't know if that's true uniformly over convex. You don't? Do you know?
I had thoughts about this, but I don't have like the proof.
Yeah. Well, maybe in the literature there's proof. I just don't know. Yeah, possible. What we will do is we take just rectangles as a measure of simplicity. So by simple rectangles, they're pretty wide. So if you think of rectangle as a bracket, like if you have a sample, then you can ask any kind of statistical question about any age bracket and any income bracket or something like this. Middle age, young age. So that's already covers a little bit of statistical tasks. Okay, good. So that was the idea how we went around this. Now let's do it a little bit more formally what exactly is high probability, what exactly is proportionality, and so on and so forth. So formally is this: the number of points in each set is a binomial random variable, because each point is when you throw a point, you can think of this as a trial. Either it falls into the set, a success, or it falls outside the set, a failure. And then we just count the number of successes as classic binomial. N trials, n points, probability of success, which is probability of getting into the set, is just the area of the set. So this is our notation. This is area of I, and this is the number of points in I. Actually, we can skip. Sometimes we can just skip I if it's obvious which set it is. So then let's see. The expected value of the binomial is n lambda, np, which is n lambda, which is great. It's exactly saying that the expected number of points is proportional to the area. And when you look at the variance of the binomial, it's np times 1 minus p. So it's n lambda times 1 minus lambda. And I'll skip the last term just for simplicity. It's n lambda. So by Chebyshev's inequality, we know that the number of points with high probability, so let's say, so Chebyshev, I'm still repeating the last class, by the way, that's why I'm a little faster here. So with probability 0.99, let's say, the number of points equals its mean, which is n lambda, with this margin of error proportional to the standard deviation. And the standard deviation here is the square root of n lambda. So if capital C is like maybe 1,000 or 100, I can maybe 100, that's true. So that's what we can expect. The number of points is high probability for a given lambda. So for a given lambda, for a given I, sorry, given set I. Okay, good. So now we're hoping that the set is that this thing, whether it's true or not, uniformly over all rectangles. I. So it's almost true. And here is as a result. So this is a non-trivial theorem on, let's call it the discrepancy theorem. Statistical discrepancy. So uniform. So this means that with probability, at least 0.99, let's say, doesn't matter. The set of the points is good. And how good? It means that any rectangle has its proportional share of points. Okay. So with probability 0.99, let's say what we have. The set of n random points is good, and good means the following. For any rectangle, actually axis-aligned rectangle, it's not rectangle like this or this, right? Rectangle like this. So any axis-aligned rectangle we have this, the predicted number of it. Okay, I actually, it's a little embarrassing, but I haven't seen this theorem in the literature. I'm sure this is proved in the literature somewhere, but I haven't seen the theorem in the literature. So I just thought it was true. I proved it myself, and I got what I got. And so maybe someone else can, maybe you can do a little bit better here. But this is what I got. Lambda in. That's the obviously the average number of points, the mean expected number of points, plus c root lambda in log n. So I lose a log factor somehow, and log factor usually people think it's okay to lose. It's a very slow growing function, so that's fine. And similarly in the left hand side, lambda in minus c root log n. Okay, again, just for a full disclosure, this is a number of points in I. Lambda I is the area of I, and C is a sufficiently big constant. We can choose it. Big but absolute. Absolute means it depends on absolutely nothing. It's like 100, let's say. Can't depend on the set or number of points, geometry, anything. Actually, as long as the left-hand side is greater than 0, which is a non-trivial regime, because if left-hand side is negative, then it's empty, and the number of points is negative. Okay, is the result clear? Everything is good? Yeah. Good, so we lose log n factor, which is okay, we can tolerate that, fine. But other than that, we get the bound uniformly over all rectangles. Now we'll get to the proof, which is very interesting. But if you have any other idea of how to improve this, it'll be interesting too, because I'm not so sure. This is what I did in my 2 hours of work, and so maybe you can do this better. And again, I did it because I didn't know where to look in the literature for this. Okay, let's do it. So the proof is actually important. The proof is a first instance of a method that you will see a lot in this course, and it's kind of a common method in modern probability theory, which is called the epsilon-net method. For simplicity, we will work in dimension 1. Dimension and not dimension 2. It's just easier for me to draw the pictures there. In dimension 1 means that this is not the area, but actually it's a length of I, and it is not the square, but an interval. So we sample points from the interval, and our rectangles are intervals now. So everything is dimension 1. Dimension 2 will be in the homework. It's very, very similar. Actually, the proof almost doesn't depend on dimension. It's just easier to explain it in dimension 1. Okay, so the epsilon-net method. All right. Let's first of all try to understand what is the main difficulty here. Why is this theorem so non-trivial? What are we fighting with here? Any axis aligned rectangle. So if the rectangle was prefixed, then we know it's true, right? This is that. If we want to prove it just for one fixed rectangle, great. High probability, true. If we prefix 2 rectangles and want the task to be simultaneously true for this rectangle and for this rectangle only, still true, right? It works with high probability for this rectangle, works for high probability for this rectangle, let's say 0.99 here, 0.99 here. So it will work simultaneously for both, also with high probability. Probability maybe 0.98, but still, yeah, correct? If two events hold each with very, very high probability, then their intersection holds with high probability. Right? Similarly, if we prefix 3 rectangles, also fine. If we prefix 100 rectangles, also fine. Maybe if we prefix even, I don't know, maybe if we prefix even n rectangles, also fine. So what is the difficulty we're facing here? The difficulty is in the number of rectangles infinity. The number of rectangles or intervals in this case is infinity. There are too many intervals, infinitely many statistical tasks that we are trying to achieve at the same time, simultaneously. And that is why we cannot take what we say we could just do this union bound intersection. So what we do? It's a very simple idea, is to make it finite. Well, if the main difficulty is that we have infinitely many rectangles, let's just make it finite. And how do we make it finite? Well, it's very simple. We just discretize. Replace this interval, it's a mental trick, right? Replace this interval from 0 to 1 with a discrete interval, where the interval, all the sub-intervals can only start and end at the discrete values, like 1 over n, maybe 2 over n, 3 over n, something like this, very small. So we choose the epsilon-net, so to speak, the epsilon-net of 0, 1 with a very small epsilon. And here is a picture. This is our interval. Remember, we're now in dimension 1, so that was formerly the square, now it's an interval. And we choose an epsilon-net. Here it is. It's just a set of points with positioned evenly at distance epsilon from each other. And let's make epsilon very small. Let's say epsilon, well, I don't know, 1 over n to the 10 maybe. So this epsilon-net looks like this: 0, and then 1 over n to the 10th, 2 over n to the 10th, 3 over n to the 10th, and so on, and it goes on until 1. So I'm replacing it with this, replacing the continuous interval with a discrete interval. And we only can now, let's, again, still a mental trick, and now let's only consider the intervals that are allowed to start and end at these net points. So let's say it's a net interval. We call a net interval the interval whose endpoints belong to this net. For example, I don't know, maybe this one. Just drawing an interval. Like that. Epsilon is 1 over n to the 10th. Okay. So here is now the architecture of the proof. We will first prove the theorem for net intervals. Why is it in principle easier? Is that because the number of net intervals is not too large. The number of net intervals is not infinity anymore. How many of them are there? What do you think? Just approximately, we don't need the exact. So each of the endpoints, how many ways are there to choose one endpoint, let's say, left endpoint?
N squared?
And, yeah.
N times n minus 1. Like,
yeah, maybe even divided by 2, because there is, yeah. But really, it's like n squared. You're right. So if there's n possible positions for one endpoint, there's n ways to choose it. and n possible positions to choose the other endpoint. So at most n squared, you can do better. It's like n times n minus 1 over 2, but we don't care about that. Only with one addition. The number of points is not n, it's n to the 10th now, right? Because the interval has length 1 over n to the 10th. So it's got to be 1 over n to the 10th times 1 over n to the 10th, which is 1 over n to the n to the 10th. N to the 10th, which is n to the 20. And this is how many net intervals. Thank you. Okay, so the number of, this is why it should be at least possible to prove that theorem, because now we're having, well, maybe a lot, but still a polynomially many number of the net intervals. Then we will do that. And then after we prove it for the net intervals, we extend the theorem for all intervals by approximation. And this is, let me just give you an example. So maybe if I want really to prove the theorem for this interval, for the black one, I just approximate it with the net interval with an error epsilon. And I hope that the number of points will not differ too much between the two. Okay, and that'll be the proof. Good. Is the general architecture clear? So we discretize the interval, that's called epsilon-net. Now we're facing a finitely many tasks. We do that, and then we extend by approximation. Cool. Very good. So there will be steps. First step, how do we prove it for, let's say, each net interval? So first, this first step is called concentration, where we use Chernov's inequality. We fix any, let's say, fix one net interval. I. Let's say its length is lambda. And we already said many times it's a number of points and it's binomial with mean lambda n. And so Chernov's inequality and we will use one of the forms for small deviations. I'll recall what it is from last class, maybe 2 classes before, is the following: probability that the binomial random variable deviates from its mean, lambda n, by at least delta mu. This is the mean. Delta mu is less than, let me remember, 2e to the minus delta squared mu divided by 6, I guess, or something like that. You may have forgotten this already, but this is a Chernov's inequality, one of the forms of Chernov's inequality that says how things deviate from the mean. Okay. Okay, good. Let's see. So far, so good? Okay, so how do we choose delta now? Delta is totally in our hands. We can choose it arbitrarily. And we will choose it, well, because I can tolerate this lambdas from this form. It's clear how I choose delta. They just want this thing to be that error, the claimed error in the theorem, lambda and log n. So we choose delta, whatever delta is, c root lambda n divided by lambda n, let me think, and delta would be, I believe, c log n over lambda n. Okay, so what about the right-hand side? Delta squared lambda n in the right-hand side, that's c squared And lambda n cancels. C squared log n over 6, I believe, or something like this. Yeah, so C squared log n, okay. Yeah, I think it's good. So probability that ni minus lambda n deviates larger than C lambda n log n, that's what we want to control, becomes e to the minus C squared log n over 6. Good. Now C, capital C, is in our hands. This is the C's from the theorem. We can choose it arbitrarily large, but absolute constant, like 200, 100. So we can always choose it maybe larger than 1,000 or something like this. And we get e to the minus log n, which is 1 over n, to an arbitrarily large power. Let's say 100. I can always do that by choosing C, a large but absolute constant. Good. Okay, let's just think of what have we done? Now we're just doing it on the instance level, just to fix one net interval, and for that one net interval, the probability of failure for this theorem, the probability of failure is super small, 1 over n to the 100. So each fixed interval is good with very high probability. The number of points there is correct with extremely high probability, and we don't have too many of these intervals to control. Now we can do the union bound to control all of them simultaneously. Like there is n to the 20 n to the 20 net intervals. Each of them is good with extremely large probability, 1 over n to the 100. And so we can take the union bound. And that's step 2. It's a union bound, where we say, right, each interval is good with high probability, therefore all of them simultaneously can be good with high probability. So if we call, let's say, this event a bad event, let's call this event BI. The bad event, the event that thinks that the conclusion of the theorem is false for that specific interval. So that's very bad event, but very small probability. All right, so union bound. How does it work? Again, very important step, by the way. Probability that there is at least one bad interval, and that's what we do not want to have. There is a bad net interval. Is a probability of what? What shall I put here? Intersection or union of the BIs, of the bad events? BI is an event, is the event that this specific interval is bad. Now, how do we formulate the probability that there exists a bad interval? Yes, Olga is right. Again, he's right. You should speak up also, whatever. Union, right? So that's union of BIs. Existence corresponds to union. Perfect. And probability of the union is obviously less than the sum of probabilities. The sum is over net intervals, and there's n to the 20 terms here. Each term is smaller than 1 over n to the 100. And so we have, when we multiply this, we get still a very good, I don't know, 20 over n to the 100. That's a small number. Let's say it's less than 0.01. N is large. The number of points is large. Maybe we need an extra clause for that extra assumption, right? That the number of points is larger than 100 or something. But that's okay. Okay, as you're good with this? Yeah, okay, we achieved already a milestone here. We proved this theorem already. We proved the statement, just not for any rectangle, for a net rectangle. The statement says that with probability, let's make it up pass to the complement. So this means that with probability at least 0.99, all net intervals are good. I'm just reformulating it as a complement. And what does good mean? It means that the opposite to the bad event happens, which is this. For any net interval. The theorem is proved now, but just not in full generality, just for the net intervals.
May I ask a question?
Yes, Maxim.
Should we add the condition that n be sufficiently large in the theorem?
Yeah, we should. The n is large, you said, right? I didn't hear the last part.
Yeah. So should that be in the theorem somewhere?
It should be, yeah.
Oh, okay.
The way we proved it, it should be in the theorem, right? So it should. We should say assume that n is larger than c, where c is again a large constant. Maybe n is larger than 2, maybe is okay already. Maybe n is larger than 2 is okay.
You mean that for small numbers we can choose the c in the inequality sufficiently big that it's good enough? I guess.
Yeah,
Okay.
yes, Maxim. All we needed here is this. So yeah, I agree. The way we proved it, we need to assume that n, like n to the 80, is larger than 10, and that's, I think, is true for n equal 2 and up. But we could get rid of that too, I think, with a more careful bound. I just had to, instead of 1 over n to the 100, I should have put maybe 10 there in the denominator. Maybe if I put like 100 in the denominator. So we can avoid that assumption as well, that n is large. But you're right, the way we proved it. Yeah, if we worked a little bit harder, I could get rid of that. But that's not really. So you're right, but it is not really an important assumption. We can definitely throw it in statistical framework. Of course, n is large. We have a sampling with a large number of points. So yeah, let's put that. Yeah, thank you for that comment. It's useful. Any other comments? No? Good. So at this point, we can kind of almost celebrate because we proved the theorem, just not for all intervals, for net intervals. This is the situation here. Let me copy this. And this is I is the net interval here. Maybe do it this way. This is I, the net interval. Perfect. Now, how do we pass it to all intervals? Transfer the result to all intervals is by approximation. This is the last step is the approximation. Suppose we have now any interval. And we approximate it by the net interval. That's it. That's the entire proof, basically. So for any interval, J, it lies in a net interval. It's approximated on the outside. In the net interval, I, that has a little bit larger area. Maybe this time we should distinguish between lambda, what lambda means. So lambda I and lambda J will be different this time. So lambda I is less than lambda J plus, what's the error? Well, this error, 1 over n to the, this error is epsilon, and this error is epsilon. So at least 2 epsilons, and epsilon is 1 over n to the 10th. So the area is going to be just that in the worst case. So the length satisfies this. Correct? Good. And now the completion of the proof just in the next line will just say, well, they're so close. The net interval and the true interval. So the number of points between them is really, really close. Right? The number of points that follow in this interval is almost close, and that's how we transfer it from net to entire. So let's do this formally. The number of interval in J, that's what we need. Obviously less than the number of interval in I, because that's a larger set. We proved the result for I. So this is because I, by the previous step, because I is good. We should assume that this event holds, right? Don't we? Let's make this in blue. I'm making this. So assume this holds. This good event holds with high probability. Assume it holds, then we can go on with these inequalities. And that's basically it. Lambda. Now we have to transfer everything to J back from I to J. So that's lambda J plus 2 over n to the 10th. N plus C root lambda J plus 2 over n to the 10th. And log n. Okay, and now I have to fight this parasitic terms and get rid of this terms n to the 10th. How can we do this? So this is lambda Jn plus 2 over 9. Okay. Next term. In the next term, I also can separate. If you guys can remember this inequality, maybe you root of a plus b is less than root of a plus root of b. I'll apply it here. I just want to separate the square root into the main term and the error. The main term is obviously this. And the error is lambda. Yeah, the error is this. Okay. It's just a, sorry, a little technicality, but they're just trying to push the errors in one place and then control them together. Okay, and now we kill this term. We want to say that it's too small, this error term. And of course it's too small. It's 1 over n to the 9. So it's even smaller than maybe 1, which is smaller than the error term lambda j and log n. And so we can combine this two terms together. And that's it. And that is the end of the proof now. The third is a little technical, but it's like saying that the intervals are so close, that this lengths are close and the points are close. And that gives us everything. I think that's it. Yeah. So that's a proof. It's called the epsilon-net method, and it consists of choosing the epsilon-net, so discretizing the problem, passing from infinite number of tasks to finite, then use concentration to control each task, union bound to combine these tasks, an approximation to pass from discretization back to the original problem. It's very archetypical proof in modern theoretical data science.
So in the first part, we just choose C from the inequality, right? And then when approximating, we just make another C, which is 2C, right?
Yeah,
okay.
you're right. Yes. Yeah, good question. So we actually proved it was 2C instead of C. And we already used C somehow, so we kind of conflated the meanings of this. Maybe if I wanted to make this proof like publishable or completely rigorous, we should have, let me make this in red. We should have, what should have we done? I guess we should have done this, not C, do you see this? But C over 2 all the time. Don't try this down, it's a waste of time, but start with C over 2, because, in anticipation that later we'll multiply by 2. We get the original C. So that's, but how do we know that before we finish the proof? That's the problem. It's only after we finish the proof do we know that we need to divide by 2. So I think that would be the full rigor of this. C over 2, C over 2 here, C over 2 here, C over 2 here, and that becomes C. Okay. So we should have allowed ourselves a little bit of room for C initially, but we didn't know that, of course, until we finished the proof.
I have another question about knowing things before the proof. So you said that you came up with this inequality by yourself, and I have a question: how do you know to write the logarithm down and then it holds? So,
oh yeah, very good question. Yeah, perfect. Thank you, Maxim, for asking. Yeah, well, of course I didn't. Right? If I guess first, I guess yeah. That's important. How do you actually think about this thing? Well, first of all, you think that this is true. Like you're hoping that this is true over all intervals. Right? That's the ideal hope, possibly not realizable, but you think that, well, that's the best possible thing. So you're hoping that you can prove it without the logarithm factor. Then okay, then we write that. Then what I do, I write Chernov's inequality. Here I still don't have to think about logarithmic factor, right? It's just vanilla Chernow inequality, nothing like that. And then we realize that in order to make this simultaneously over the epsilon-net, I need this less than the number of points in the epsilon-net. Sorry, the number of the net intervals. So I need this to be small, not just small like 0.01. That'll be too few, because we'll have to then, this small probability has to then fight the union bound, how many net intervals we have. Remember, we multiplied it. So this probability has to be really small, smaller than the 1 divided by the number of net intervals. You still okay? Yeah. Now the number of net intervals, well, I believe should be at least n, the number of net intervals, as much as the number of points, because n, you see that if you make the number of net intervals, then the interval of length 1 over n is about the same as scaling the distance between the adjacent points. So in order to capture the correct number of points, we need something like that, 1 over n at least. And if we want this to be less than 1 over n, then it's pretty clear that we need an extra log factor. Because why do we need an extra log factor? Is because lambda n, that's just the number of points that fall into the interval. That could be very small. It could be a constant. We can't rely on that because we're doing overall tasks. So we can't rely on that being large. So this could be a constant. Maybe I'll just read it out like this. And yeah, and we just need a lot less than n. How do we do that? Well, we need to get log factor inside this exponent to make that happen. So that was kind of way of thinking about this. Okay, that comes with of course with my prior experience with these problems. That usually the idea is like this: as long as your probability bounds, your power in probability is exponentially good, and here our power of probability is exponentially good. So Chernow's inequality is super good, exponentially. It gives you exponential small probabilities. As long as the power of probability is exponentially good, you can prove results by losing only log factors. That's a general understanding of in the theory. And so, but that said, I do not know what it really means to lose log factors. So my original idea, and maybe it's true, maybe you guys can do this. My original idea was that the following inequality is true: root of log n plus c root log n, which is better, right? You just add instead of multiplying by log n. Maybe you can do that. I'm not so sure. That will be much better. Yeah, Maxim, did I answer your question kind of?
Yeah, definitely. Okay, thanks.
Sure. Okay, just to complete this whole story. This is for statistical sampling. This result holds for statistical sampling. And it says that the number of points equals to in each interval, for any statistical tasks, now we're good, equals the correct number, just the expected number, plus or minus one, the deviation, the standard deviation also is unavoidable because of the statistical error. That's our statistical error. And what we do lose, what we do pay for things being uniform is a log factor. Okay, fine. You can ask different questions, not in the term statistics, but maybe in theoretical in computer science, in coding, in cryptography. What if I can choose the points, not by sampling them at random, but I can deliberately, deterministically choose where to place the points inside 0, 1. In statistics, it would be, what if I, instead of sampling from population, I choose deliberately which people to pick? Not completely random, but I choose them. So it's kind of a designed experiment. Can we then improve the quality? And the answer is yes, actually. So if we do this, one last remark. If we choose, if we are allowed to select the endpoints deterministically, and we can design the sampling. So sample design, if we can do that, then we can do much better. And I would be equal to, well, proportional to the area that we know. So it's lambda in plus or minus. And remember, we had the first term here was root of lambda n, the statistical error, which is unavoidable, something like that. But we can kill that. Plus or minus, I can't remember log n or root of log n, but I think it's log n. This is amazing results. It goes way better than statistical sampling, right? Because instead of root n, you get log n, which is much, much smaller, much better accuracy. So overall I. And that is one of the main results in geometric discrepancy. And I linked actually to this lecture, I linked also a book that's called Geometric Discrepancy. And this is the first result in that book, if you're interested. It's very deterministic, very easy to understand how the proof works. And that's the whole area. Good. I am done for today. Do you have any questions or other comments?
Question about homework.
Homework, yes. Okay, let's stop sharing now. I'm sorry, the people who are watching us online, let's stop sharing now. Homework questions.